Cosmos Policy: Fine-tuning video models for visual motor control and planning. Open source video generation models like NVIDIA's Cosmos can generate diverse robot videos given input images and text. Can we post-train these models to also generate actions that control a robot? In this work, we introduce Cosmos Policy, a robot policy fine-tuned from the NVIDIA Cosmos Predict 2 video model. We post-train Cosmos to predict not only future images, but also robot actions and values. There are two modes of deployment for Cosmos Policy. A, just deploying the policy by itself, or B, deploying the policy with model-based planning using the future state and value predictions. Cosmos Policy deployed just as a normal policy without any planning achieves state-of-the-art performance in the LIBERO simulation benchmark with a 98.5% average success rate. Cosmos Policy also achieves state-of-the-art performance in the RoboCasa simulation benchmark, outperforming prior methods with significantly less training data. Here we show the actual images observed during rollouts in the top row and the futures that Cosmos Policy predicts in the bottom row. The future image predictions are not needed outside of model-based planning, but they can provide useful visualizations of the policy's intent. Now, how well does Cosmos Policy work in the real world? Let's see it in action. Here we see that Cosmos Policy can perform language-conditioned pick and place following the user's prompt. Here, Cosmos Policy performs a long-horizon, contact-rich manipulation task, folding a t-shirt with many steps with only 15 training demonstrations. Here, Cosmos Policy performs consecutive object placements, handling a training dataset with high-action multimodality given random alternations of left arm versus right arm usage. Here, Cosmos Policy operates with high precision and carefully grasps and opens a Ziploc bag before putting a candy inside, a seemingly simple task that is more challenging than it looks. Overall, in our real robot evaluations, Cosmos Policy shows strong performance, even outperforming recent vision language action models such as Pio5 and OpenVLA OFT. Going further, once the policy evaluations are complete, the recorded rollouts can be used to further refine Cosmos Policy's world model and value function. Then, Cosmos Policy can better plan action trajectories with higher likelihood of success through model-based planning. For example, we show how Cosmos Policy can do best-of-n search with n equals 3 samples for illustration. First, the current state is fed as input into Cosmos Policy, which generates n candidate action chunks. Then, Cosmos Policy's world model predicts the resulting future states, and its value function predicts the future states' values. The highest value action chunk is selected and deployed on the robot, and the search is repeated for the next action chunk. It is also possible to extend the search tree by auto-regressively rolling out the world model and querying the policy on the predicted futures through multiple layers. We can get the value prediction in the last layer, use that to select the highest value branch, and deploy the first action chunk in the branch. Let's see how model-based planning can help on challenging test cases where the base policy has trouble. Here, the base Cosmos Policy struggles to grasp the candies and ultimately places just 1 of 5 candies into the bowl. However, with model-based planning, Cosmos Policy makes greater progress and fetches 4 out of the 5 candies. In another task, we see that the base Cosmos Policy sometimes fails to maintain its grasp of the Ziploc bag while opening it. However, we find that planning can help avoid common failure modes like this. The planning policy avoids the mistake and continues on to successfully complete the task. Here we show the futures that the world model predicts during a rollout after we refine the world model using policy rollouts. We observe that the actual futures tend to follow the predicted futures throughout the episode. Now we show examples of future state and value predictions seen during model-based planning. Given the current state, Cosmos Policy generates n candidate futures. For simplicity, we just show 2 candidates, with a search depth equal to 3. The value function assigns higher value to the future on the right, since it shows better progress towards opening the Ziploc bag. Let's see another example. Here, the futures are more semantically similar, but the value function prefers the more confident prediction on the right. In general, the differences between predicted futures can be subtle, but these subtleties can compound and affect the episode's outcome, even if they're not obvious to the human eye. Fortunately, a learned value function provides a data-driven way to search through even subtle differences to achieve a better outcome. Overall, we find that model-based planning improves Cosmos Policy's completion score by 12.5 points on average across challenging settings. To see how Cosmos Policy works and learn more about it, please visit our website. Thank you.